Hi guys, how you doing? I'm going to talk about properties of materials, and for those of you who remember from my original talk, this is talking about stress, strain, energy per volume, strong, weak. That's the kind of ideas because each kind of material has different properties. Say elastic, different properties to say plastic, different. And so I'm going to talk about strength, if they're brittle, stiffness, flexibility, elastic, plastic, toughness, and weakness. But essentially, these are opposites. This is strong is opposite to weak, brittle is opposite to malleable, stiff is opposite to flexible, elastic and plastic, kind of opposites, I'll show you soon, and toughness. So, without further ado, here is our graph. And this is the basic graph, force against extension. There's also a stress versus strain, but we'll get onto that in a second. First, we'll talk about strength and weakness of this graph, because this graph kind of makes more sense. So, if something's strong, what do you think it means? Something strong, it kind of makes sense that it takes more force to get to the top. Hey, Charlie, come over here. Can you stop pencil sharpening? You can come watch with me. I'm going to teach you physics, okay?
Okay.
Okay, come sit here. Okay, so this one's strong, okay?
Yeah.
Yep. This one's stronger because it takes more force. That says force. And then if it doesn't go up as high, if it doesn't take as much force to break, you see it takes a lot of force to break there. It takes less force over here. This is less force to break.
Okay.
So that's weaker. Okay?
Yeah.
So
the tall one is strong
yeah.
and the lower one is
Weak.
weak.
That's awesome. So if I want to draw it, the higher it is, the stronger it is. Okay?
Stronger?
And the lower it is, the weaker it is. Awesome. Now, if this is force against extension, we also have a stress versus strain, which you might also understand. And you may get a bit confused, but it's easy if you just remember that stress equals force over area. So the more force it is, the more stress there is.
Oh.
And strain equals change in length over length. So the more extension there is, the more strain there is.
No extension.
Extension means it gets longer.
Oh.
Or changes, okay? So you can use them in the same kind of way. So if an object is higher up on this force before it breaks, that means it's stronger. If an object is higher up on stress before it breaks, that means it's stronger. So this is stronger than that too, right, Charlie?
Yeah.
Yep, you can understand?
Yeah.
Awesome. Okay. So, and that's on the scale. All you need to do is look. It's on
How
the scale
come you
of
want
stress
words there?
and force. So that they can understand, so I don't have to mess up my page.
Okay.
Okay, you want to go now?
Yeah.
Okay, nice. Okay, so for brittleness and malleability, that's looking at this side, extension, or looking at strain. Okay, so the more brittle it is, like you think about it, if you get something really brittle, like a piece of cement, and you try and push it, it just breaks. Okay, you try and bend it, it just breaks. It doesn't really move at all. So it doesn't get extended. So this breaks when it doesn't move very much. It just breaks immediately. So that is more brittle. Whereas something that can bend a lot is known as malleable. So an elastic band is very malleable. So if I had to look at this one is more brittle because it breaks quite fast. This one's much more malleable because it can go on for a long time without breaking. So if we really want to have a quick way of doing this, on this side it's brittle, on this side it's malleable, and we're looking at this is a strain and length. Okay? Now stiff and flexible, it's just a measure of how hard it is to move something. If it takes a lot of force to move it this far, obviously it's very stiff, because stiff objects are very hard to bend. Whereas if it takes much less force to move it, this moves 5 times 10 to the minus 4. This is how far it's moved. And this is less force. Whereas object Q will only move a tiny amount compared to the same amount of force. So Q, the gradient, is much higher, so it's much more stiffer. So stiffness equals high gradient, flexibility equals low gradient. Stiff. And elastic plastic regions, too hard, but elastic means it'll go back. It's just in the linear region, so all the way up to here. See, it starts to not really go linearly anymore. It's not straight anymore. So this is now plastic. This is like, elastic is like this. It'll go back to its original shape. And like all the way up to here, it's elastic. But once it starts to stay out of shape, then, where's my water bottle? My water bottle is not here, but if you imagine pressing into the water bottle, it stays out of shape, and that's a plastic region, like plastic water bottle. So elastic is the linear region, and plastic is the moldable region. Finally, toughness is just the area under the curve. Oh, not for this though. Toughness is the area under the curve for stress against strain. Okay? That's how much energy per volume. So just remember that energy per volume is stress against strain. That's toughness. Energy per volume. Or looking at a stress strain, it's the area under the curve. Okay? That's what toughness is. If it's a force by distance, the area under here is just energy. Okay? So that's all the terminologies. I'll show you a quick example of how to use them in the next video. Well, maybe I'll show it to you now. A little bit lazy. Okay. From this graph, compared to hard steel, soft steel can be described as hard steel is more stiff. Soft? Okay, so which one's stiffer out of these two? This is a higher gradient, so hard steel is more stiff. Which is stronger? Well, along this scale, you know, strength is going up and down. Hard steel is stronger because it's higher up there. So soft steel is not stronger. Brittle. So which one can go further along this scale? Because remember brittle, we look under here. It's along the scale. If it's more to the left, then it's more brittle. If it's more to the right, then it's more malleable. And we look, soft steel is more malleable, so it's not more brittle. Hard steel is more brittle. Ductile. So, ductile is the same thing as malleable. Ductile. So we can see soft steel is more malleable, is more ductile than hard steel. Because the hard steel is stiffer than soft steel. So hard steel undergoes less plastic deformation than soft steel. That's a measure of brittleness, okay? Because this is plastic deformation. A greater stress is needed to fracture the hard steel than soft steel. That's a measure of strength. Because a greater stress, now we just look at here, stress is to do with strength. The area under the graph is greater for hard steel than soft steel. So the area under the graph is related to toughness, okay? So that has nothing to do with stiffer. The gradient of the stress strain curve is greater for hard steel than soft steel. Stiffness is related to the gradient. So therefore, hard steel is more stiffer than soft steel because the gradient is higher. Which of the following statements about toughness is correct? Soft steel is tougher than hard steel. Yes, that's true. Because that's all the area here. Just quickly over it. Nah, that's not true. Nah, because the area of hard steel is much less than the area of soft steel. We don't need to know the volumes to know the toughness. Because toughness is independent of volume. Yeah, and so that's a quick outline of how all these strong, weak, brittle, malleable, stiff, flexible, elastic, plastic, and toughness works. You just look at the axes. Summary, strong, weak is stress. Brittle, malleable is if you look across horizontally, this is up, down. Flexible is the gradient. Toughness is the area. And elastic, plastic is just where along the curve it is. Great. So I hope that helps. I'll catch you guys later.